طيب بسم الله الرحمن الرحيم. We started talking about the physical layer, and as we said, there are two distinct functions for the physical layer, which are حد فاكر؟ The two distinct functions of the physical layer are encoding and encoding means decoding, and framing is data link layer, and signaling. Okay, encoding and signaling, and we said encoding is to convert each group of bits into another group of bits, and we'll talk about why we do that. And signaling talks about the fact that we convert the ones and zeros, the individual bits, into analog signals or digital signals, as we will see now. So actually, we started talking about signaling before encoding. So first, we'll talk about signaling. It's as if we're going in the physical layer from bottom up. So first, we'll talk about signaling, how we convert the bits into a digital or analog signal. And we said that this can take three different forms based on the three fundamental characteristics of any digital signal. These characteristics include the amplitude, the frequency, and phase. So whether we vary the amplitude, so we convert the bits into varying amplitude signal, or varying frequency signal, or varying phase signal. So one example of the varying amplitude schemes or mechanisms is what we call non-return to zero signaling. By non-return to zero here, we mean that for each bit, you have a continuous amplitude to represent what this bit is. So if it's 1, this gets represented using a positive voltage, let's say like 5 volt or something. If it's 0, then it's represented using 0 signal. It's non-return to 0 because it does not have to return to 0 at every single bit. So depending on the value of this bit, if it's continuous ones, like if it's 1, 1, 1, then you don't actually return to 0 at every bit at all. So it's a continuous horizontal line to represent fixed voltage. So this is a very simple signaling mechanism. It's very easy to implement. So whenever you have, if you have like 1, 0, 1, 1, 1, 1, let's say. So this is simply 1 is positive voltage, and then 0 is 0, and then 1s are fixed voltage like this. So it's very simple, very easy to implement. The circuit that you need to implement this is very simple. So this talks about the fact that we convert the bits into a digital signal. Digital signal means that the signal takes discrete amplitudes, whether it takes positive voltage, not like something like this. This is a continuous signal. It's not a digital signal. So so what is the problem with this signaling mechanism? This signaling mechanism has a number of problems. The first one is that this signal uses the bandwidth inefficiently. So why is that? Well, it turns out that this square kind of signal gets converted in the frequency domain into something like this. So whenever you have continuous signal with sharp downturns like this actually turns to have like high frequency components in multiple frequencies in the frequency domain. So So this spans very large frequency spectrum, which means that it takes significant amount of bandwidth to be represented in the frequency domain. So even though you are actually representing one bit using one continuous signal like this, but in terms of frequency response, it takes a lot of bandwidth. So that's why this encoding or this signaling scheme uses the bandwidth inefficiently, because the bandwidth spectrum tends to be quite large. Another problem is that it's very susceptible to electronic or electromagnetic interference. Just because of the fact that we have very wide spectrum here. So another bit will be represented using another frequency signal like this. So you cannot actually separate the signals from each other. So they tend to interfere with each other. So this is reflected, for example, on the time domain. On the time domain, this is reflected using, if you have like any noise in the signal itself. So when you receive the signal on the receiver side, this signal becomes sometimes like this. So the sharp downturns, they tend through like some noise to take these continuous values, because these sharp turns are very hard to pass through any channel. So through the interference, this will be deformed. The signal will be deformed like this, and the signal in that form will be very prone to noise. Why? Because sometimes the difference between this high amplitude and this low amplitude, it tends to shrink a little bit. So sometimes for the receiver, it's hard to distinguish the one from the zero, because they tend to have close amplitudes. So sometimes you may incorrectly decode the one as zero or the zero as one. Okay? So this type of signaling scheme, even though it's simple, but it's susceptible or it's prone to electromagnetic interference. Another problem which is very obvious is that the boundaries between the individual bits can be eliminated completely. Like imagine if you have like a continuous stream of ones. So this will be represented using a continuous signal like this. Okay? So it's very hard for the receiver to recognize where the boundary of each bit. So you can actually decode 5 ones or 4 ones as 3 or 5 ones as 4, because the boundaries of the bits become very hard to recognize, right? Because it's a continuous signal, right? So if there is any clock drift between the sender and the receiver, it's you can easily recognize, or you can easily miss one of the bits, right? So how can we enhance this? Just to make this even clearer, how can we enhance this? We can enhance this by trying to enforce that you have to have a change of amplitude within each bit. Okay? If you have a change of amplitude within each bit, then the receiver can take this change of amplitude as a verification step for the receiver to say, okay, I have one change of amplitude here, so this is a separate bit. Okay? So even if the receiver has any clock drift on its side, it can recorrect itself through this amplitude change. So because it recognizes that since I have an amplitude change in this bit, then the other amplitude change must be a separate bit, and so on. So it resynchronizes its clock back and eliminates any clock drift on the way. The non-return to zero does not have this cool feature, because if you have stream of ones or a stream of zeros, then you end up with continuous signal. So it doesn't have any change of amplitude within each bit. It does not maintain that. And that's why we call it non-return to zero, because there is another coding scheme which is called return to zero. So in which case, even if you have continuous ones, so this will be represented like this. So this is one bit, this is another bit, and this is the third bit. So 1 will be represented like this. Okay? And then if you have 0, then it goes all the way. And then if you have 1, so you have to return to 0 every time. So you have to return to 0 and then go like this. And if it's 0, you go continuously. So in each bit you have to return to 0 regardless of the value of this bit. So for each bit you have to return to 0 all the time. So this creates a change in the middle of the bit, which the receiver can use as a verification for it to work correctly. So the non-return to 0 has all these problems. To fix this, there is a very common signaling scheme, even though it's called here encoding, Manchester encoding, but in fact it's a signaling scheme or a signaling mechanism. So this Manchester encoding takes the concept of varying phase, or it represents the 0 and 1 using varying phase, and basically it represents the 1 using a change of amplitude like this, and the 0 the same signal but with 180 degrees phase shift. It's like it's reversed. So the 1 is like this, and the 0 is the mirror of it. So this tends to fix most of the problems of the non-return to 0 encoding scheme. This change within the middle of each bit helps the receiver to distinguish clearly. So if it's going from negative to positive, okay, then it's 1. If it's going from positive to negative, then it's 0. Detecting the changes, okay, it's much easier compared to detecting just an amplitude, because as we said, due to noise, the amplitude tends to tends to shrink a little bit. So the 5 volt maybe becomes maybe 3 volt or something like this, and the 0 volt may become 1 or 2. So the difference becomes a little bit vague. Whereas if you have a change within the middle of the bit, then the signal tends to have more changes along the way, which helps the receiver to detect the 1s and 0s with higher probability of success. So that's why this simple encoding mechanism is used in the 10 base T Ethernet. It's a very simple mechanism, and it solves most of the problems with the non-return to 0 encoding scheme. Okay, so what about the encoding? So this is enough about the signaling. So we talked about signaling, and we discussed the 3 forms of signaling, whether we vary the amplitude, we vary the phase, or we vary the frequency. We talked about one example for varying amplitude and one example for varying phase. We didn't talk about any example for varying frequency. The other distinct function of the physical layer is encoding. And encoding talks about the fact that the bits or the stream of bits that come from the data link layer, we have to convert each group of bits into another group of bits. So we take every 4 bits, for example, from the bit stream coming from the data link layer, and we represent it using 5-bit group. So, well, so when you mention this, when you discuss this, then someone might say it doesn't make any sense. Why do I have to represent 4 bits into 5 bits? Okay, so what is the point? It looks to us like it's an overhead. It's not needed. I don't have to do that. But there is a logical reason why we need encoding. So encoding has lots of benefits. So this is an example that talks about taking 4-bit code and convert it into 5-bit symbol. Okay. Then we take this 5-bit symbol and then we use Manchester encoding or non-return to zero to convert it into digital signal to transmit it over the physical medium. Okay. So we take each 4 bits and then we convert it to 5-bit symbol. If you notice in this table here that the one cool feature in this encoding is that the number of changes in the bit from the 4 bits to the 5-bit is increasing. Okay, so for example, if I have imagine if I have a continuous stream of zeros using the non-return to zero signaling. This will be a 0 voltage signal continuous, right? If you take the 5-bit symbol, then the 4 0 bits become a 4 ones and 1 0. So you have introduced 1-bit change. So that compensates for the fact that even if you are using a signaling mechanism that's very prone to noise, like the non-return to zero, you can use the encoding to compensate for that. Yeah. Okay? To introduce more changes in the bits in such a way that helps the receiver to detect the boundaries of the bits and detect that this is 1 and this is 0. Because the more changes you have within the bits, the better or the higher the probability of detecting this on the receiver side. Right? You cannot control the data coming from the application layer that they have to have stream of ones and zeros, with a specific number of changes, but you can do that as part of the physical layer by encoding and decoding. So you can encode, and then once you receive on the receiver side, you can get it back to the original bits. So this is one important benefit we gain when we do encoding. So introducing more changes in the bit. The other benefit is that we limit the energy transmitted. Again, by changing by introducing the changes in the bit, because if you have like stream of ones, for example, stream of ones tends to have positive signal all the way. So positive signal means that the average voltage will be high, right? The average voltage tends to be, whereas if you have change in the bits, so you tend to have positive and negative. So the average voltage tends to be low. The average voltage goes towards the 0 voltage. So if the average voltage goes towards the 0 voltage, then the average power, okay, which is proportional to that voltage, the average power tends to be low. So by introducing these extra changes in the bits, we can reduce the average power by introducing these changes. In order for us to introduce more changes in the bits, we have to have an overhead. So the cost that we had to pay is that we had to increase one extra bit. So if we had to do this, then we better utilize this to the maximum, right? So having 4 bits will give us 16 different combinations, right? From all zeros to all ones, right? Having 5 bits will give us a combination of 32. Okay, so we have to use 16 bits to correspond to 16 combinations of these 32 to represent the original data, right? So we are left with some combination of bits which are not used to represent the original bits. So what can we do now is that we can actually use these extra bits as control signals. Okay? So we can use these extra bits as control signals between the data link layer and the physical layer. One important example is the start of a stream or the stop of a stream. Remember we talked about start frame and stop frame, right? So we said that start frame and stop frame is nothing but a special combination of bits. Okay? So, I mean, one might ask, who guarantees that this combination of bits will not be part of the data itself? Yeah. Didn't you ask yourself this question?
Yes.
Okay? So chances are this will never happen because of using the encoding. Because of the fact that in the encoding we take each 4 bits and we convert it to 5 bits. So we guarantee that the combination used for start and stop frame will never be used as part of the data because we control that through the encoding and decoding. Okay? So that's another benefit from using encoding and decoding, which makes encoding and decoding a must as part of the physical layer. So these are the 3 major benefits of encoding. Even though we are introducing extra overhead, but we can do it in such a way that we can actually, instead of increasing the bandwidth, we actually can reduce the bandwidth a little bit. We can reduce the average power in a way. And we can use the extra bits as control signals between the data link layer and the physical layer. And this will help us implement the interface between the physical layer and the data link layer.
Doctor, why do we have two symbols for start and 2 symbols for end?
That's a good question. Start of stream, yeah. That's a very good question. I don't know. It may be like you have 2 values. You can use any one of them. So you have the possibility to use any one of them. There must be a reason for this from the error detection point of view. There could be, but I don't know specifically what the reason is.
And the way we generated from 4 to 5, is there some formula like XOR and 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 OR?
Well, that's another good question. It's a lookup table, so you are free, but the rule of thumb is that you have to introduce an extra change. So I have to gain an extra change. So for example here, I do not have any change in the bits. So here I have 1 change. So if I have 2 changes here, I have to have 3 or more. Okay? So the rule of thumb is that you have to increase the number of changes. Otherwise, you didn't gain anything.
Yes.
Okay? So that's the main rule. There is no specific formula that you can apply. No, but there are some rules that you can use. Okay? So based on that, we can define the capacity of a system using one of these 3 fundamental concepts. So we very commonly talk about bandwidth, and we talk about throughput. What's not very much as common is to talk about goodput. Okay, so what is the difference between these 3 things? So we mention bandwidth a lot, and we less frequently talk about throughput, and we don't know the difference between the 2. Well, bandwidth talks about the theoretical capacity of a specific medium. Okay? Theoretical means that you can almost never achieve this theoretical bandwidth. So this is the actual theoretical bandwidth which talks about the physical layer stream of bits that you can transfer using this physical medium. Okay? It's usually measured as kilobits per second or megabits per second and so on. Okay? So for example, like 10 base T Ethernet. 10 base T has a theoretical bandwidth of 10 megabits per second. 100 base T has a theoretical bandwidth of 100 megabits per second. So what does that mean? This means that the actual bits that you can transfer over the Ethernet is 100 megabits per second. However, this doesn't mean that this is the speed that you're going to get. Why? Because, well, as we have studied in data link layer, well, the line itself, first of all, it gets shared by multiple machines. Okay? Even if one of them is sending at one single point of time, this machine will almost never get the 100 megabits per second. Okay? So they measure this theoretical bandwidth, assuming perfect channel, which is dedicated for one single machine, okay, with absolutely no sources of error. Okay? They measure this bitrate theoretically based on some calculations. So they know that, for example, I'm using non-return to zero signaling scheme. So the signal rate is this. Okay? So this signal rate, assuming absolutely no error, this means that the actual theoretical bit rate is this. That's it. As simple as that. But of course, what happens is that, as we said, there are so many sources of errors. Some sources of errors are like interference, bit loss, collision from the MAC layer point of view. Okay? The environment may introduce some, effects, some interference, some noise, some distortion, deformation to the signal. Okay? So, even without interference, sometimes I actually send the bits and there is some kind of collision, or if I send the bit, the receiver on the other side will not be able to decode it because the signal has some bits in error, so it has to drop it and so on. So there is some probability of packet loss due to any of the sources that we talked about. So that tends to happen a lot on any physical medium, not only wireless. Of course, wireless is very much prone to noise and very much prone to all kinds of noise that we talked about, whether interference or distortion or deformation and so on. And it happens easily on wireless because it's traveling over the air. By the way, bandwidth is measured over wireless, again, assuming that you have a specific signaling rate, okay, and it assumes that there is a vacuum. There's no actual, there's not even air, it's a vacuum. So there is absolutely no sources of error. So this is bandwidth, but throughput takes into consideration all sources of interference, noise, MAC layer protocol limitations, like if there is any collision and so on and so forth, right? So if the theoretical bandwidth is X, maybe you can get maybe 0.6x or 0.5x or 0.7x. This is the actual throughput that you're going to get, which means that the successful bits that you get on the receiver side is maybe 60%, 70%, something like that. Okay? So what about good put? Well, remember that this 60% or 70% is the actual bits, okay? And we have lots of headers in this stream of bits, right? We have the data link layer header, right? We have the network layer header, we have the transport layer header, we have the HTTP header, and we have all these headers are overhead. So good put talks about the actual useful data at the application level that we get on an actual network. Okay? So the good put talks about the usable data from the application point of view. So you have to remove all the headers from the data link layer all the way to the application layer, which is considerable amount. Remember, TCP has maybe 20 bytes, IP has 20 bytes, and so on. And data link layer, I don't know, it has like significant amount of bytes depending on the protocol in the data link layer. In the application layer, HTTP, it's a big header. It's text-based, so there is a good amount of overhead added to the data in order to transmit it over the network. So if you remove all this overhead, what is the actual good put? This is what we refer to as good put. An example, like over the Ethernet LAN, 100 base T, the actual bandwidth is 100 megabits per second. But if you actually try to send, even using one single machine, without having to have multiple machines trying to send at the same time, even with one single machine, you may end up with a throughput of 60 megabits per second. Only like 60% or 70% of this theoretical bandwidth will be useful or will be used, which is what we call throughput. From this 60 megabits per second, if you remove all the protocol overheads from the data link layer all the way to the application layer, you may end up with an actual good put of 40 megabits per second. Which means that the overhead of the different protocols in the different layers may get as much as 50% in some cases. Okay? So any questions? So this is the difference between the theoretical bandwidth, throughput, and good put. The other part of this chapter talks about cabling. And of course, you have covered, or at least you will cover, cabling in the lab. So here we have different types of cables. We have the copper media, and we have, of course, fiber optics, and we have wireless. So the copper media talks about any kind of cable that uses copper as part of its components. And these copper media are divided into two major categories. One is the coaxial. Coaxial talks about the fact that you can use one single copper wire, thick wire, okay? And it has all types of shields, as we will see. Whereas twisted pair talks about the fact that instead of one thick wire, you have multiple, you have 8 different small wires, okay? And they are twisted. They call it twisted pair.
So each two together?
Yeah, each two together.
Does this increase the rate of transmission?
We'll talk about that. It's a good guess. Yeah. We'll talk about that. Well, first of all, depending on each type of cable, the connectors that are used, they change completely. For example, the coaxial cable, we're familiar with the coaxial, which is the one that we use at home for the TV. So it has special types of connectors, right?
Yeah.
Whereas for twisted pairs, we know the RJ45, the plastic RJ45 that we use it for Ethernet to hook up. Okay, so these connectors, they tend to change from one type to another. The UTP cables, for example, or the unshielded twisted pair, and we will talk about why it's called unshielded, because there is shielded twisted pair. These are some examples of the unshielded twisted pair. There is UTP Cat5, and there is UTP Cat5e, and there is UTP Cat6. For example, this one is used for the 100 base T, or the Ethernet with bandwidth 100 megabits per second. This one is Cat5e. It's usually Cat5 is used for faster Ethernet. For example, this one is used for fast Ethernet or 100 base TX. TX here refers to the fact that this is Cat5, and it's also used for 100 base T. 100 base T means that you have a theoretical bandwidth of 100 megabits per second. Okay, for Ethernet. Base here refers to baseband. Baseband meaning that the signal is not transmitted using like high frequency, like in the case of wireless. In the case of wireless, we use 2.4 gigahertz or 5 gigahertz and stuff. But here, the signal, when it goes through the coaxial or the unshielded twisted pair, it tends to be in a very low frequency range, which is what we call baseband. So the signal is not modulated to higher frequency. And T refers to the fact that this is a twisted pair cable. So there are certain differences between coaxial and unshielded twisted pair. Generally speaking, the thick wires, they tend to have like wider frequency range in terms of the frequency of the signal that goes through this cable. If it's thick copper, then the frequency range becomes wider. So this makes the coaxial cable capable of carrying signal with wider frequency. This turns to be a very wide frequency. I think in the case is in the range of like 500 megahertz as a wide range, whereas for shielded and unshielded twisted pair, it tends to be a lot less than that. However, remember for the twisted pair, each wire has a small bandwidth, but we have 8 of them. So we can use 4 of them for one direction and another 4 for another direction, right? So you have separation for full duplex communication, okay? And even though each wire has a shorter range of frequency, but we have 4 in parallel. So the 4 in parallel can in fact have higher bitrate compared to coaxial. Okay? So even though coaxial, the single wire has wider range of frequency, but with the twisted pair we have 8 wires, so we can actually support higher bitrate, higher actual bitrate. Okay? Whereas for coaxial, we can have an analog signal with wider frequency going through the coaxial cable. Another difference between the two types of cables is that each one of them, they use certain isolation in a different way. So if we look at the coaxial cable, we have one isolation, one plastic isolation, and another what we call braided isolation. Okay? So this plastic isolation tries to limit the energy of the signal inside this wire to dissipate outside. Okay? So it tries to focus the energy that goes through the wire to be inside this wire. When you focus the energy, this means that the energy is not wasted by deviating outside. Whereas the braided isolation here tries to protect the wire from the outside interference. So one is trying to protect it from dissipating. The other one is trying to protect it from the outside effects. And the outside here, this is called outer jacket, which is just packaging for everything. So this is the isolation for the coaxial. For the shielded twisted pair or unshielded twisted pair, we have the isolation done in a different way. So, well, we have plastic isolation for every single wire, right?
Every single small wire, a fat wire, or
Very thin wire.
for the thin wire or the wire?
No, for the thin wire, For the thin wire, we have, again, this plastic isolation is to protect the energy from the signal going through the wire from dissipating outside. The same effect of this. But here, of course, the plastic isolation is a lot thinner because the signal that goes is again lower frequency. But why twisting? That's this is an interesting thing. That twisting is actually done to not protect it from interference, but to balance the interference. Well, what happens is that if you don't twist, then you have two wires like this, right?
Yes.
So in that case, if the effect of the interference from above is more than from below, then you have more interference on this wire, more than this wire, right? So if you tend to twist it, then the same interference on average will affect the both wires. So this is important to kind of balance the signal that goes through the wires to have the same amount of interference, if any. Of course, we will try to protect it from the external interference as much as possible, but if there is some interference, then we balance this interference by doing the twisting. The shielded twisted pair does not stop at this point and tries to protect each pair of wires by introducing another plastic isolation for each pair of wires. So this is to protect it from the outside. But why do we commonly use unshielded twisted pair and not use the shielded twisted pair? Unshielded twisted pair is more commonly used. And the only reason for that is that by doing this plastic isolation, they found that the effect of this plastic isolation after the twisting becomes minimal. On the other side, you are introducing higher cost by having to have this plastic isolation, right? So the shielded twisted pair tends to be more expensive with no actual reason for protecting, because the twisting already balances out the interference and it turns out to be enough as a protection.
But Dr. the twisting, there is some mechanism, like which two you choose, or just random?
Yeah. Have to. Well, yeah. We'll talk about that. So that answers your question. So, of course, the wires tends to have specific colors, green or strip green, and so on, and then you have to put it in sequence according to this color or this color. This is called the T568A and T568B. So you have two different configurations, and if you have the same configuration on both sides, then this is what we call a straight-through cable. Yeah, and if you have if you have one configuration from one side and another configuration from one side, this becomes a crossover. So each one of them is used in a different application. Okay, each one has a different type of usage. Okay, so we'll stop here. We'll continue next.